Discussed about the Parseval's theorem for periodic signals. Can you tell me what is Parseval's theorem for periodic signals? If xt is a periodic signal, the average power of the signal is equal to what? What is Parseval's?
Summation of average power of all the components.
It is a k square, isn't it? This is the Parseval's theorem. Here, the left-hand side, we have the average power. We are considering a periodic signal xt with period t naught. Then the average power, this is the average power of the signal. And on the right hand side, we have seen that it is the sum of the average powers of the harmonics, isn't it? Okay. So that's how we find we can find the Parseval's theorem for periodic signals relates the average power of the signal to its Fourier series coefficients. How we can find the average power of a signal using its Fourier series coefficients. Similarly, for an aperiodic signal, when we talk about an aperiodic signal, we talk about the energy of the signal. This is the energy of the signal. Okay. Now let's see how this is related to if xt, this is the relation xt, xj omega. Then the energy, this is the energy of the signal, and how this energy of the signal is related to its Fourier transform, x of j omega. Okay. So we can write this as isn't it? Xt into x star t, that is mod xt square, energy of the signal. Now, can you tell me what is this integral? Integral minus infinity to infinity xt x star t into e to the power minus j omega t dt. Is it the Fourier transform of this?
Yes.
It is the Fourier transform of this signal. Is it? Now, what is the Fourier transform of xt into x star t using the properties? This is equal to, is it this? 1 upon 2 pi x of j omega convolution x star minus j omega.
Yes, sir.
Yes. Okay. This one. Now we want to find the energy of the signal. Tell me, how is it related with this? Energy of the signal. Is it somehow related with this?
At omega 0.
Okay. Remember, you cannot directly substitute this omega here. Okay. It is the convolution at that particular instant of time. If you substitute this value, you will get a constant. Okay, that is wrong. First, you have to find the convolution for omega is equal to 0. It is not directly substitute here x of j0 convolution x of minus j0. It is not. Okay. Now, what is this integral? 1 upon 2 pi integral minus infinity to infinity, is it x of let me write it as x of ju into x star minus, there is a minus sign here, then you have to replace omega with omega minus u. Is it this integral? Is it the convolution integral?
Yes.
This is a convolution integral. Now you have to find this for omega is equal to 0. Is it? So what is that? 1 upon 2 pi integral minus infinity to infinity x ju into x star ju du when omega is equal to 0. Is it? I'm putting omega is equal to 0 here. Then you get this. Can we simplify this? Is it this?
Yes, sir.
So that is the Parseval's theorem. It says that energy of the signal, sorry, this is the energy of the signal, this is small x, that is equal to 1 upon 2 pi. This is the energy of the signal. Okay, we can find the energy of the signal from the from its spectrum or Fourier transform of that signal. Okay. So we can see that this is the energy of the signal is, if you sketch x of j omega squared by 2 pi, then it is the area under this, isn't it? Energy of the signal is area under this x j omega square 2 pi, is it? So that's why generally this is called this x j omega square. This is called, if you sketch this as a mod x j omega square, if you sketch this as a function of omega, it is called the energy density spectrum. Energy density spectrum. Okay. It is called the energy density spectrum. Okay, first let me write these expressions here. If we have a signal xt, its Fourier transform x of j omega is integral minus infinity to infinity xt e to the power minus j omega t dt, and xt is 1 upon 2 pi Okay, now first let me explain what is duality property. We have seen many examples. Like if we have one of the examples is a rectangular pulse. If we have a rectangular pulse in the time domain, what is the shape of the spectrum? In the time domain, and this is the frequency domain. Frequency domain means Fourier domain. Okay. If we have a rectangular pulse in the time domain, what is the shape of this that spectrum? Spectrum means if you plot x j omega as a function of omega, that is called the spectrum of the signal. What is the shape of the spectrum? What is the Fourier transform of a rectangular pulse?
Sinc function.
It is a sinc function, isn't it? It is a sinc function. Okay. Then we considered this example also. If the spectrum, if this shape of the spectrum is this, a rectangular pulse in the frequency domain, what is this? What is the signal in the time domain?
Sinc function.
It is a sinc function, isn't it? It is a sinc function. Not only this example, let's say this, if it is delta function in the, what is the Fourier transform of delta function? Fourier transform of delta function is 1. And if we have an impulse in the frequency domain, what about this? Its inverse Fourier transform. It is 2 pi, sorry, no, it is 1 upon 2 pi, isn't it? 1 upon 2 pi. So here also you can see that if in the time domain it is an impulse, in the frequency domain it's a constant. Here in the frequency domain it is an impulse, time domain it is a constant, isn't it? So it seems that there is some inverse relation. Okay. So for understanding this duality property, so let me write first thing you have to understand is that the small x and capital X are two functions. Okay. It is not that this capital X is something associated with the frequency domain. It is just a function. So we can say that if the Fourier transform is a mapping from one function into another function, isn't it? Small x to capital X, is it? Here in the time domain, we are considering it as a function of t. And here, okay, j, there is slightly confusing. Let's say it is x of j omega. So this is one function and this is another function. Okay. So the duality property states that if we have a signal in the time domain that is having this shape, we can have a time domain signal having this shape. Think only about the shape. Don't think that this capital X is something associated with frequency. Okay. Suppose we have a signal having this shape in the time domain, then what about its Fourier transform? Is it somehow related to this function? That is a duality
Yes.
property. That is a duality property. So think this Fourier transform pairs as mapping from one function to another function. Small x is one function and capital X is another function. Okay. So now let us derive that property. Let me start with this x of j omega okay. That is the Fourier transform. Now can I write this as is it changing the variable? Is it?
Yes.
Can I write this as no, this is wrong. It is wait x of j omega xu into j omega. Oh, okay, I'm replacing omega with this. Okay, so we can write it as xu into this one. It is tu, isn't it? Is it?
Yes, sir.
So can we write it as x of jt integral minus infinity to infinity x omega e raised to j. There is a minus sign here, isn't it? This minus sign minus j omega t d omega. So here I am changing the variable. What am I doing here? That change of variable. Now look, this is a function in the time domain xjt. It is a function in the time domain. Now we have to find the Fourier transform of this signal. Can you tell me what is the Fourier transform? If you compare these two. So I add one more step. X of minus omega e to the power j omega t d omega. Now tell me, what is the Fourier transform? Here, if xt is a signal and if x j omega is Fourier transform, then this is the relation, isn't it? 1 upon 2 pi into, this is the inverse Fourier integral. Here, this is the time domain function, x of jt. Now tell me what is the Fourier transform of this? Is this inverse Fourier integral?
2 pi into x of minus omega.
Is it x of jt? Its Fourier transform is what? 2 pi into
X of minus omega.
X of minus omega, isn't it? Is it 2 pi into x of minus omega?
Yes, sir.
Because if you find the what is the inverse Fourier transform of this, if the Fourier transform is 2 pi into x of minus omega, the inverse Fourier transform is 2 pi into integral minus infinity to infinity 2 pi x minus omega e to the power j omega t d omega, isn't it? That is this integral. So can we say that x of jt and 2 pi x minus omega, they form a Fourier transform pair? That is the duality property. The duality property says that if we consider a signal xt, and let's say its Fourier transform is x of j omega, this is the duality property. Sorry, this is small x, there is a scaling factor 2 pi. So forget about small x and capital X. So duality property says that if you consider if we consider a signal in the time domain that is having this shape, that shape of that function is small x, and its spectrum is capital X. Okay. Now the duality property says that if we consider a signal having this shape in the time domain, what is its spectrum? What is the spectrum of that? If you consider a signal having small x, that shape small x, for example, this one, rectangular pulse. And in this case, this capital X, this function is a sinc function, is it? Now, if we consider in the time domain a signal having this shape, that is this shape, what is its spectrum? How is it related with this? Is it 2 pi times flipped version of this? Here in this case, since this is an even function, we are not observing the effect of that flipping. I will explain, I will show you some examples where there is a flipping operation. Okay, so let me prove this example. This one. So let me write it here. This is the duality property xt Fourier transform x of j omega. Then if we consider a signal having this shape in the time domain, that means you replace omega with t. Then its Fourier transform is, its spectrum is related to the small x, that is 2 pi into, sorry, there is a flipping operation, minus w. Okay, this is the duality property. Let us consider this example. This is xt, 0, t1 minus t1 and 1. What is the Fourier transform exact expression? Do you have the formula sheet?
2t1.
Consider a signal of this shape in the time domain. That means you replace omega with t. Consider these signals 2 sine t into t1 by t, isn't it? Here it is a function of omega. Now we are considering a function in the time domain having that shape. So replace omega with t. Now what does it say? What is the this one? Fourier transform? What is the duality property? X of minus omega, is it this? This is a function of omega, and this is 0, this is t1 minus t1, and there is 2 pi. Is it the duality property? There is a flipping operation. Since this is an even function, even if you flip that, you will get the same signal. Is it?
No, sir.
Now, if you rearrange, if you simplify this expression, will you get the standard form? If you look at the formula sheet, the standard result is given if there is a W minus W1 WT by W, WT by pi t, isn't it? Is it that? Please verify. It is WT by pi t. This is the standard result given in the formula sheet. Are we getting the same here?
Yes, sir.
We are getting the same because T1 is a constant, W is a constant. If you replace this with W, so what we get is omega W minus W2 pi. This one will be 2 sine T W by T, isn't it? So 2 and 2 will get cancelled and this pi can be brought here. So it is sine T W by pi T. That is this form a Fourier transform pair. We have proved it. Is it? Let us consider another example. Let's say e to the power j omega naught t. What is the Fourier transform of this? E to the power j omega naught t. It is 2 pi into delta omega minus omega naught. Is it? Here omega naught is a constant. Now what is the dual of this? Duality property. You have to consider this in the time domain. 2 pi into delta t minus omega naught. Omega naught is a constant. That is a constant. That is what? Tell me what is duality properties? This xt, x of j omega, then x of jt, it is 2 pi x minus omega. This is duality property. So here I change the variable omega to t. We got a time domain signal that is 2 pi into delta t minus omega naught. Here omega naught is a constant. Now what we have to do? What is Fourier transform according to duality theorem? Is it 2 pi into what? 2 pi into
Is to minus j omega not omega.
e to the power minus j omega naught omega. Okay. So here it is a constant in the time domain. So let us can we write like this 2 pi delta t minus t naught, that is 2 pi e to the power minus j omega no, j omega t naught. Is it that? That constant I am changing to t naught because now it is a constant in the time domain. So let's say it is better to write it as t minus t naught. So here it is e to the power minus j omega t naught. Delta t minus t naught, what is a Fourier transform? What is the Fourier transform of delta t? Is it 1?
Yes.
Fourier transform of delta t minus t naught? 1 into what?
E to the power minus j omega t.
That is what we have shown here. We started with this property. Using duality property, we derived this. Okay. So for applying this duality property, if you are given a Fourier transform pair, let's say small x is the shape of the signal in the time domain and capital X that function in the frequency domain. Now if you consider a function having this shape in the time domain, its spectrum is related to this small x. This is how it is related. That is called the duality property. X of jt is 2 pi x of minus omega. And in some of the textbooks, you will see that this duality theorem is written in this form. Are they same?
Yes, sir.
They're the same. Using the reflection property, you'll get, so these are same. Because if you replace t with minus t, you have to replace omega with minus omega. That is the time reflection property of Fourier transform. Okay? Flipping property.